Okay, so we are going to move into kind of the second lesson in chapter 11. And before we actually get started on it, just going to ask the question, what do you call that thing?
A rotary lock.
Okay, yeah, you can call it a rotary lock. Anybody else know what else you can call this thing? Begins with a C.
Combination.
Most people would call this a combination lock. Now I got to ask you, say that your combination on this thing was, I don't know, 5, 17, 34, right? Well, if you entered it in as 17, 4, or 534, would it open? If this was your combination and you did them in this order, would it open the lock? The answer is no. Order matters, right? These things are completely and totally misnamed. They should not be called combination locks. They should be called permutation locks. Because when we were doing permutations, let me just scroll back to the original definition here. Okay, we got to go back further than that. The definition of a permutation is it's an arrangement. The number of possible arrangements. So when you talk about how many different ways things are arranged, the order matters. What we're going to look at today is combinations. And in a combination, what makes a combination different than a permutation is that a combination is a selection of objects where order doesn't matter. So calling this thing a combination lock is ridiculous. The order that you put the numbers in matters. So they never, I guess when they named them, they didn't ask any mathematicians. Here's a good example. Let's say I want to form a group of 3 from 4 students. I have student A, B, C, and D. Alfred, Betty, Charlie, and Dave. The only combinations are ABC, ABD, ACD, BCD. Note, why did I stop counting? Because notice that ABC is the same as ACB, or BCA, or BAC, or CAB, or CBA. Those are all the same 3 people. If the order that I select them in doesn't matter, I have a far smaller number than I would have had if I was counting arrangements when I was doing permutations. So, for formula, if you have n items and you want to take r items, but not arrange them, the number of combinations is NCR, which is the permutation formula, divided by another r factorial. So notice everything kind of, let me get the highlighter out. Notice that this part of it right here is the permutation formula, and then you just divide it by another r factorial. And there's a shortcut way to write this, like if this isn't shortcut enough, you'll see this very often. And very often people will kind of say this as, I should probably flip into tab mode here. N choose R is what you'll very often hear people call that. So let's start with some math here. There are 14 females and 8 males in a class. You want to form a group of 5. How many groups can be formed? So this is 22 choose 5, right? 14 plus 8 is 22. So there's 22 people. I would like to pick 5 of them. So according to my formula, that is n factorial, which is 22 factorial, over 22 minus 5 factorial times 5 factorial. That simplifies down to 22 factorial over 17 factorial, 5 factorial. And then you can punch buttons. So on my calculator, I will, there you are. I will go 22 math probability 4. So 22 factorial divided by, and then don't forget, I need a bracket so that the calculator knows both of these are denominators. 17 math probability 4 times, I already know what 5 factorial is, but I'll punch buttons. 5 math 4 close brackets equals, and there we go, 26,334. I don't mind in a calculation like this if you shortcut it. Again, most calculators, most scientific calculators have a choose button. It might look like this. It might even look like that. Look for a button that has that on it. On this calculator, I believe I'd have to go 22 and then go to math. And again, it's stuck in the probability section. And there we go. It's number 3. N choose R. And then it should give me the same answer. So if you can find the combination button on your calculator, again, it might look like that. It might be an NCR. It's probably a shift somewhere. I have seen a couple calculators that have it like this. So look for that button. Most scientific calculators do have it. Okay, that was a very basic question. Let's make it a little more challenging. How many groups can be formed if you have to choose 2 females and 3 males? So why don't we just think of it as 2 separate things? Out of the 14 females, I choose 2 of them. And out of the 8 males, I choose 3 of them. Oh yeah, and what does the fundamental counting principle tell us? If you're trying to do 2 different things, what's the chance they both happen? Or what is the number of different ways they can both happen? You multiply them together. And here for sure, I would use a calculator. I would literally do this as 14 math. This is probably easier on your calculator. You don't have to go to this stupid menu. Choose 2 times 8 math. Choose 3. And I don't think you need brackets or anything. Hit equals. Yeah, that's the number I got the first time. 5,096. Okay. How many groups can be made with Joseph, 1 other male, and 3 females? Now, I know this may sound weird, but you don't have to actually calculate picking Joseph, right? There's only one way to pick a specific person. So I guess you could say that picking Joseph is 1 choose 1. And if you do the math on that, what's 1 choose 1? Well, let's see. That would be 1 factorial divided by 1 minus 1 factorial times 1 factorial. And, well, 1 factorial cancels 1 factorial, leaving me a 1. And, that gives me 0 factorial. And hey, remember how I said the other day that we have to define 0 factorial as 1? Well, now you can see why. You can't divide by 0. You can't have an impossible, undefinable number, especially when you're doing something that you know has a probability of 1. There's a 100% probability that if I have a hat and I throw Joseph in the hat, what's the probability that when I reach into the hat I draw out Joseph? 100%. This has to be 1. Right? Therefore, 0 factorial must be 1 by definition. So anyway, we're not going to bother ever writing 1C1. While we're at it, what do you think anything choose itself is? Forget just 1 and 1. Let's think about this logically. Let's not use n maybe. N's maybe a confusing number. Let's use x and r. So the formula is n choose r is n factorial over n minus r factorial times r factorial. So what happens if I have x choose itself? And I was trying to write an x there, and I wrote an r because, you know, my brain's not functioning properly. There we go. What if I have that? Any number choose itself. Logic would dictate that if I said, okay, I'm going to throw the names of 10 people in a hat and then draw 10 names, everybody's going to look at themselves and go, boy, this is the easiest contest to win ever. And you're going to say, well, isn't there a 100% chance that everybody here is going to win? And so how many possible combinations are there? 1. And then there's people going, well, wait a minute, you might pick this person first and that person second. Those would be permutations. If order mattered, it's a permutation. Order doesn't matter. I throw 10 names in a hat and I draw 10 names. Shouldn't there be one way to do that? So this should turn out to be 1. So that's x factorial over x minus x factorial, x factorial. And once again, you end up with 1 over 0 factorial, because of course anything minus itself is 0. And since I know that the answer to that has to be 1, then 0 factorial must be 1. So there we go. If anybody watched the video I put the link to, I think they have a similar argument to that. Anyway, so we're going to ignore Joseph. Joseph, it's a 1. Ignore that. Timesing by 1 is silly. But I still need one other male. So now I'll say 7 choose 1. Get it? Because there were 8 males to begin with. Joseph is out of the running. We've already picked him. I need one more male out of 7 possibilities. Times, and I need 3 females. So how many females were there? 14. 14 choose 3. This is interesting too. What do you think 7 choose 1 is? 14 choose 3, I think I'm going to use a calculator. Well, maybe do I need a calculator for this one? I'm going to try it without a calculator. 7 choose 1 is 7 factorial over 7 minus 1 factorial, 1 factorial. And 14 choose 3 is 14 factorial over 14 minus 3 factorial, 3 factorial. Okay, let's simplify the one on the left. That's 7 factorial, which is 7 times 6 factorial. Why did I do that? Because I could already see I had a 6 factorial on the bottom coming. Are you okay if I don't bother writing 1 factorial? You know, 1 times itself is, 1 is just 1. Or anything times 1 is itself, I should say. And now over here, 14 factorial, that's going to be 14 times 13 times 12 times 11 factorial. Now, why did I bother doing that? Because what's 14 minus 3? 11 factorial over 3 factorial. And I see some cancels. So, can I do this without a calculator? Maybe. I have 7 times 14 times 13 times 12 divided by 3 factorial is 6, right? So 6 goes into 12 twice. And now I have 7 times 14 times 13 times 2. I might still grab a calculator for that. I don't know what 7 times 13 is. 7 times 7 is 49. 49 times 52 is what that calculation is. What's 49 times 52? I think it's 20. I already have the answer sitting right here. It's 2548. There we go. Okay. Make that a little more readable there. There we go. Okay, so there's our first example of a combination problem. Why don't you try one now? Actually, you'll try 2. How many ways can the store manager hire for 3 identical positions given 12 candidates? Number 2, the chess club has 9 grade 10s, 5 grade 11s, and 14 grade 12s. The club's coach must select a team of 2 students from every grade to compete in a tournament. How many possible teams could she select? Okay, I'm going to pause the video, give those questions a try. Okay, we're back. And here we go. How many ways can a store manager hire for 3 identical positions given 12 candidates? 12, choose 3. I wouldn't use a calculator for 12, choose 3. I mean, I could. But that's 12 factorial over 12 minus 3. That's a minus. Factorial, 3 factorial, which is 12 times 11 times 10 times 9 factorial over 9 factorial times 3 factorial. Those cancel. 3 factorial is 6. So 6 goes into 12 twice. And I'm looking at 22 times 10, which is 220. Okay, so that's definitely the kind. As you can probably guess, we'll have two parts to the test for this stuff. One part where you're allowed a calculator and one where you're not. That would be one that I'd expect you could do without a calculator. As soon as the numbers start getting well past your times tables and into the thousands, then yeah, we probably would just let you have a calculator. Okay, for number 2, we need to choose 2 grade 10s. 9 choose 2. And means multiply in this stuff. We need to choose 5, or out of 5 grade 11s. We need to choose 2 of those. And then out of 14 grade 12s, we need to choose 2 of those. That I would just run through the calculator. 9 choose 2 times 5 choose 2 times 14 choose 2. Give it a try. You should get 32,760. Is that the number you got? Let me know if that didn't work for you. Okay, just like yesterday, the story doesn't end there. It gets more complicated. First, just like we did yesterday with permutations, what if we introduce algebra? And again, those of you who are double dipping, who also did an applied course, this is the part that's pretty brand new to you. You probably didn't do this kind of fancy algebra. Okay, so we're going to simplify this thing. Well, here's how we're going to start it off. We're going to start it off by showing that, well, according to the formula, this is n factorial over n minus 5 factorial, 5 factorial, and we're dividing by n minus 1 factorial all over. Now careful here. This is n minus 1 minus 3. I'll actually write it out. N minus 1 minus 3 factorial, 3 factorial. Okay, I don't like looking at that complex fraction any more than you do. So how do you divide when you're in fractions? Well, you take the numerator, and instead of division, you multiply by the reciprocal of the denominator. So this fraction here flips over. So it'll have the 3 factorial, and then I'm going to simplify this. N minus 1 minus 3 is n minus 4 factorial, all divided by n minus 1 factorial. There. That looks much prettier. Now, I'm going to start simplifying. Now remember that we learned yesterday that n factorial is, let me just move over and remind you of that, n factorial is n times n minus 1 times n minus 2. I can keep doing this all day. Times n minus 3 times n minus 4, dot, 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 until I get to 3 times 2 times 1. So I can kind of cut this anywhere I want and just say it's n times, in this case, n minus 1 factorial, right? Because everything, any place you stop is still a factorial after that. So if that makes sense to you, I am going to switch this up. I'm going to say that n is n times n minus 1 factorial. And I'm going to say that n minus 4 on the top here, factorial, is n minus 4 times the next number smaller, which is n minus 5 factorial. And then there's still a 3 factorial on top. And then on the bottom, there is I'm going to leave n minus 5 factorial alone, but I'm going to break 5 factorial into 5 times 4 times 3 factorial. Are you okay with me just combining these? I mean, I'm multiplying, right? And then over here I have n minus 1 factorial. And u cancel u, right? Anything divided by itself is 1. U cancel u, and u cancel u. So I am left with n times n minus 4 over 5 times 4 over 20. And there we go, simplified. If you prefer, you could say n squared minus 4n over 20. Right? So there we go. Let's try another one. Let's solve. This time, do you see the difference between the instructions? Simplify means get to the smallest possible piece of algebra that you can. Solve, this is an equation this time. This time I'm actually looking for a value for n. So this is equation solving. So I have 2 times n choose 2. So n factorial over n minus 2 factorial 2 factorial, which equals n plus 1 factorial over n plus 1 minus 3 factorial 3 factorial. Okay, what do we want to do with this mess? How about we go 2 factorial is 2, so 2 divided by 2, that cancels. That makes life easy right there. Then how about, you notice that, maybe I'll just rewrite this. Notice that this is the same factor in the denominator. I don't know why I made that so long. There we go. This is the same factor in the denominator on both sides. Right? N plus 1 minus 3 is n minus 2 factorial. So I can multiply both sides of the equation by n minus 2 factorial. And now I think I'll multiply both sides of the equation by 3 factorial. So I get the equation 3 factorial times n factorial is equal to n plus 1 factorial. All right, enough with the factorials. This, of course, is 6, and n factorial can be n times n, whoops, I'm going to leave that one alone. N factorial is going to be left alone. On this side, that can be written as n plus 1 times n factorial, right? Think about it. If I start with a number that's n plus 1, by the same kind of reasoning as that, n plus 1 factorial is n plus 1 times n minus 1, until I get down to just the number 1. So that means I can now divide both sides of the equation by n factorial, and n is 5. And you could do a check to see if it worked if you wanted to. All right? So let's play the game again. Let's pause and let you try those couple questions. So guys at home, I'm going to stop the video, so pause your video and give these a try. All right, I'm going to start going over these. If you need more time, pause the video some more. But here we go. Simplify that. Remember, simplify means I'm just going to get it to as simple a piece of algebra as I can make. So this is n minus 1 factorial over n minus 1 minus 3 factorial, 3 factorial. And we're timesing that by 1 over n minus 2 factorial over n minus 2 minus 3 factorial, 3 factorial. Okay, once again, this thing here hurts my eyes. 1 divided by a fraction is like just reciprocaling the fraction. So I have n minus 1 factorial. I might as well simplify that to n minus 4 factorial. 3 factorial. There's the left fraction. And the right fraction, when I do the reciprocal thingy, is going to have n minus 5 factorial, right? Because that's what this is, n minus 5. And times 3 factorial, all over n minus 2 factorial. And now I can see clearly now. The 3's are gone. And I can do some simplification here. N minus 1 is bigger than n minus 2, so I'll start with n minus 1. N minus 1 times n minus 2 factorial. N minus 4 is bigger than n minus 5, so I'll start with n minus 4 factorial and turn that to n minus 4 times n minus 5 factorial. And then look at that. Isn't that nice? Bye-bye, 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 bye-bye. And that's it. This simplifies all the way down to n minus 1 over n minus 4. Isn't that cute? All right, the one on the right is an equation again. So I'm going to say this is 720 times n factorial over n minus 5 factorial 5 factorial, which equals n plus 1 factorial over n plus 1 minus 5. I'm going to just do that in one step this time. And remember, this one's just a permutation, right? So it's just, there's no extra factorial there. So it's n plus 1 minus 5, which is n minus 4 factorial, right? No extra thing here, because remember, this one's a permutation only. Okay. What do I know? You know what I know? I know 5 factorial is 120. 720 divided by 120 is 6. That made life better. And what else do I know? I know that I can maybe start expanding these. So what am I going to expand? N is bigger than n plus 1 is bigger than n. So I'm going to leave the n factorial alone. And over here I'm going to expand this to n plus 1 times n factorial. There. Meanwhile, over here, n minus 4 is bigger than n minus 5, so I'm going to expand this one to n minus 4 times n minus 5 factorial, n minus 5 factorial, and then I use algebra tricks. I multiply both sides of the equation by n minus 5 factorial, bye-bye. I divide both sides of the equation by n factorial, bye-bye. And I am left with the equation 6 equals n plus 1 over n minus 4, which I can solve algebraically. I'm going to multiply both sides of the equation by n minus 4. I'm going to move the n to the other side. Move the 24 to the other side. And there we have it. What a lovely piece of algebra. I hope you're not getting the impression that all the equations we're ever going to give you are going to equal 5. But it's like on the test, I don't know what I'm doing. I'll just say 5. Okay, so yeah, hopefully we'll mix that up in the homework and there'll be a couple that don't end up being 5. So there we go. There's the algebra. One last thing with combinations, and again, this is the same sort of process we went through with permutations. What if there's cases involved? Now, in combinations, it's actually a little harder to be able to tell when you need a case and when you don't. So the first example is going to be just a non-case example. On a test, you must answer 3 out of 5 short answer questions and 2 out of 6 of the essay questions. This is not cases. This is, I'm doing 2 different things. 5 choose 3, 6 choose 2. Fundamental counting principle tells me that I can just multiply those things together for the total number of ways I can do both things. And run that through the calculator or do the math, you get 150. Look at the difference between the first one and the second one. This one involves cases. On a test, you must answer at least 4 of the 5 short answer questions and 2 of the 6 essay questions. And do you notice the key words here that tell you that, oh, I got to deal with I got to deal with cases? It's at least. So that means that I have to deal with case 1, where I answer 4 short answers. And then case 2, where I answer all 5 short answer. And then I misspelled the word short. See why I have to calculate those separately? Now I'm going to assume that when they say 2 out of 6, that this at least only applies to the 4 out of 5, not the 2 out of 6. Otherwise they'd say and at least 2 out of 6, and then this would be a much bigger calculation. So case 1 is I am doing 4 out of 5 times 6 choose 2. And when I run that through the calculator, I get 75 possible ways, possible combinations. If I answer all 5 short answer, hey, we've seen this before. What happens when you do n choose n? You get 1. So this is just basically 6 choose 2, which is 15, right? 6 times 5 divided by 2. Add that together, and you get 90 possible cases. All right. So I'll give you a hint on the next your turn here. It's definitely a case example. So one more time, I'll pause the video and let you give this a try, and then see if you get the same answer I'm going to get. Okay, so one more pause here. There we go, we're back. While we were pausing the video, I kind of noticed that this isn't worded all that well. It says, assuming the pucks are distinguishable. No, that's kind of not what they mean. What they mean is, assuming, how about this? Assuming pucks of the same color, and then I guess I didn't need to erase the word are indistinguishable, right? In other words, a black puck is a black puck, a red puck is a red puck. It doesn't matter what. They're trying to tell you by saying that they're indistinguishable that it doesn't matter which one you pick, and it doesn't matter what order. It's not like I'll arrange them when I get them out of here. So if this was just a problem on a worksheet and it didn't happen to be the combinations worksheet, you'd know it wasn't a permutation because of the indistinguishability of the pucks. It wouldn't matter how you arrange them. So how many possible ways is there to have at least? There's what tells us we have cases. So case 1 is where I have exactly 3 pucks that are red. So 3 red pucks. So I have 6 to choose from, and I'm picking 3 reds, but I'm picking 5 pucks. So that means I have to choose 2 more pucks out of the 8 blacks. And then I'd run that through a calculator and get 560. What's case 2? Well, case 2 is where I get 4 reds and 1 black. So that would be 6 choose 4 times 8 choose 1. which is 240 divided by 2, which is 120. Remember, this is, oh, and remember, this is just 8, right? So 120. And the last case is, it says at least 3 red pucks. Doesn't say I have to have any black pucks, just at least 3 red. So what if I have all 5 are red? Then it's 6 choose 5. And then you really don't need to bother saying this, but you could say times 8 choose 0. And again, anything choose 0 is going to have to be 1. We can look at why that is in a sec. Let's finish this problem first, then we'll just quickly look at why that is. And 6 choose 5, you should know, is just 6. Okay? And add all that up, and you get 686 possible combinations of hockey pucks in the bag. Go Jets. Now, just really quick, how did I know just mentally that 6 choose 5 was going to be 6? Well, because think about it. N choose n minus 1, right? A number 1 smaller than that is going to be n factorial over n minus 1. Oh, I should put that in a double bracket. N minus, n minus 1 factorial over n minus 1 factorial, right? Okay, look at how this is going to work. This is going to be n factorial over, this is n minus n, which is nothing, but then I'm minusing negative 1, so that's going to be positive 1 factorial. And then over here, I get n minus 1 factorial. Well, 1 factorial is just 1, so ignore that. And n factorial expands to this. So there you go. How did I know 6 choose 5 was just 6? Well, because n choose any number that's just 1 less than n has to be itself. We just proved it. And the other one is, how did I know that 8 choose 0 was just going to be 1? Well, because think about it. Suppose we have n choose 0. So that's going to be n factorial all over n minus 0 factorial, 0 factorial. And what's n minus 0? It's still n. So I have n factorial over n factorial. And there's that pesky 0 factorial again, which had better be 1, or else that doesn't make sense. And you think about it. I have 8 names, I throw them into a bag, and I'm going to draw no names. How many ways can I have that happen? Well, 1, I guess. Kind of makes sense when you think about it. So there we go. That is all there is to permutations and combinations here in grade 12. This used to be a much longer unit, and we used to then go where the applied guys go. The applied guys started with this stuff, and then they applied it to probability. So guys who did the applied course, this is where we stop. It's harder in the sense than this is a little more theoretical, and you have the algebra part where you have to, actually do proofs and pieces of algebra and stuff. But remember, the hard part of this unit in applied was the probability part? Yeah, we don't do that part. Here in pre-cal, there's pretty much no probability anymore. There used to be, but they took it out years and years ago and just assumed that, well, you're smart, so you'll figure out probability when you get to university. Don't worry. The 2 worksheets are pretty much all the homework I'm going to give you on this stuff, but if you'll notice, as always, there are textbook questions that have been at the bottom as we've been going along. So if you want extra practice, these questions are all really, really good ones. And, actually make your textbook feel useful for once and actually use it every once in a while. Okay, I guess I can stop my video. That's the end of the lesson. Thanks for watching.